This video will look at ionic equations and precipitation reactions. We'll start with ionic equations. Ionic equations show individual ions rather than compounds to better represent their actual physical state. It's important to note that only aqueous ionic compounds are shown as separate ions. All other chemical species are written and balanced as normal. So if we have an ionic compound that is in a solid state, it's important that we keep it that way in the chemical equation. As well as balancing the stoichiometric coefficients, the charges must balance on both sides of the equation for ionic equations. Let's have a look at an example. Here we have calcium chloride dissolving. So it goes from a solid to its aqueous state. And so as an ionic equation, we have separated the calcium ions and the chloride ions. On this side, we have the charge is equal to 0 because it's a solid, so there are no ions here. So we'll just check that on this side we have the same thing. The charge of the calcium is +2, and we've only got one of them. The charge on the chloride ions is -1, and we have 2 of them. So the total charge on the right-hand side is 0, which is equal to the left-hand side. Now we can have a look at net ionic equations. A net ionic equation shows only the chemical species that are involved in a reaction, excluding the spectator ions. So what are spectator ions? They are the ions that don't take part in the chemical reaction, and therefore they are found on the left-hand side of the reaction and the right-hand side. So they appear in the reactants and the products exactly the same. Let's have a look at an example. Here is the molecular equation for the double displacement reaction between sodium chloride and silver nitrate. We can see that we have aqueous ions here, here, and here, and the silver chloride is the solid compound. So it is the only thing that we won't write as individual aqueous ions in the ionic equation. So let's write the ionic equation now. Okay, now you can see here that we've got sodium plus aqueous on this side and sodium plus aqueous on this side. Those are spectator ions. They're not actively involved in the reaction, so we're going to cancel them out. It's the same with the nitrate ions on both sides. It is not the same with silver and chloride because they are in the solid state here and the aqueous state here, so they must stay. Now we can write the net ionic equation. So the net ionic equation just shows the silver ions and the chloride ions coming together to form solid silver chloride. Just checking that the charge is 0 on both sides, we can see looking at this plus and negative charge here, and just a stoichiometric coefficient of 1 for both of them, that the total charge on the left-hand side will be 0, which is the same as the right-hand side. I'll just note that this is a precipitation reaction because a solid has formed from the aqueous ions, and we're going to look more at precipitation reactions now. We can use solubility rules to determine whether a solid will form in a displacement reaction. So if the rule states that an ion is soluble, then it remains in its aqueous form. If an ion is insoluble, then it forms a solid with an ion from the other reactant. I'm not going to read through these solubility rules, but we're going to leave them here so that we can refer to them in the example. So here is the first part of the molecular equation for the double displacement reaction between calcium chloride and sodium phosphate. So first of all, we know this is a double displacement reaction, so we can write our products, which is going to be calcium phosphate and sodium chloride, and I've just balanced them there. Now, how do we know what states our products have? Well, let's refer to the solubility rules. First thing I notice is this rule number 1, salts formed with group 1 cations are soluble. So do we have anything there? Yes, so sodium is a group 1 cation, so therefore this compound, sodium chloride, is going to be soluble, so we'll write the state aqueous. I'm now seeing number 6, phosphates are insoluble. So our other product here, calcium phosphate, applies to that rule. So we're going to write S for solid here. Just note that although we had a phosphate in our reactants, it was a salt with a group 1 cation, so it was still applied to that first rule, so it was soluble rather than insoluble. Okay, now we can write the ionic equation. Once again, I've just written everything, all of the ions as individual ions, except for here, we've kept our solid compound as a solid compound. Now we can cancel out the spectator ions. And finally, we can write the net ionic equation. Okay, just to make sure we've done everything correctly, let's check the charge. We've got 3 lots of 2 plus and then 2 lots of 3 minus. So we've got a total of 6 plus and 6 minus, which will become 0, which is what we need to balance out the charge on the right-hand side. So that is correct.